So what if I told you that math isn't really about numbers and formulas? What if it's actually a language, a kind of secret code that lets us translate the messy, chaotic world around us into something, well, simple and clear? Today, we're going to crack that code together.
You've been there, right? You're staring at a word problem, and you know the math itself isn't that hard, but the words feel like they're designed to trip you up. Well, it turns out that feeling is dead on. The real challenge, a lot of the time, isn't the calculation, it's the translation.
Okay, let's get our hands dirty with an example. Take a look at these two questions. On the surface, they look almost identical. And hey, they even give you the same answer, 66. But the way you get there, totally different. In the first one, that little word of is basically a command. Multiply these things. But in the second, more than makes you take an extra step. It's a whole different thought process, and it's all dictated by the language. And that brings us to our first big idea. If you want to get good at math, you have to become a fluent translator. You have to learn how to turn plain old English into the precise language of equations. And listen, this isn't just some theory I cooked up. Test prep experts, the people who work with students day in and day out, say this is the #1 hurdle. It's not the calculus or the algebra that trips people up. It's their ability to just read the question and understand what it's actually asking them to do. So what if we had a cheat sheet? Like a little dictionary for translating these tricky English words into math. Actually, why not? Let's build a quick one right now. And this is where it gets really cool. Just look at how much information is hiding in plain sight. Of becomes a multiplication sign, is becomes an equal sign. Simple enough. But then you see a word like origin. Whoa, that's not just a word, it's a freebie. It literally hands you a data point, 0, 0, on a silver platter. Same with x-intercept, that word instantly tells you that the y value is 0. The clues are right there in the vocabulary. Okay, so once we get the hang of translating individual words and phrases, what's the next step? Well, we start chaining those ideas together to build more complex sentences. Think about it like an assembly line in a factory, right? What comes out of one machine becomes the raw material for the next one down the line. It's a chain reaction. And in math, we have a really beautiful way of handling exactly that situation. It's called function composition. Now, the notation looks a little funky at first. I get it. But the idea behind P of A of t is super simple. All it means is work from the inside out. First, you solve the inner function, A of t. Then you take that result and plug it straight into the outer function, p. This airplane example makes it crystal clear. You've got one function that tells you the plane's altitude based on time, and you have another function that tells you the air pressure based on altitude. See the problem? You can't jump straight from time to pressure. You have to chain them. Time gives you altitude, and then that altitude gives you the pressure. You compose the functions to get the final answer. All right, so we've gone from single words to equations, and from equations to these chains of functions. Now, let's pull the camera way, way back and look at the big picture. Let's talk about the language we use to describe the behavior of entire systems, like the algorithms that basically run our world. Welcome to the world of Big O notation. This is how computer scientists measure how efficient an algorithm is. And here's the key. They're not interested in how long it takes to run on your laptop right now. They want to know what happens when things get huge. What happens when you throw millions or even billions of users at it? How much slower or how much more memory will it need? This is absolutely crucial for building things that can scale. And here's a fun little piece of trivia for you. The O in Big O actually comes from the German word ordning, which means order. So it's all about finding the order of the function, its general shape, its fundamental behavior. So the problem that Big O is trying to solve is really a problem of complexity. When an algorithm has dozens of steps in calculations, how on earth can you summarize its performance? How do you ignore all the tiny details and just see the big picture, the forest for the trees? So an algorithm's performance might be described by a function that looks like, well, this. It's a beast, right? A total mess of different terms, all with their own coefficients and exponents. Trying to make sense of this directly would be a nightmare. But here's the absolutely brilliant insight. As that input, x, gets massive, we're talking millions, billions. Those smaller terms like -2x cubed and +5, they basically become irrelevant. They're a tiny whisper next to the absolute roar of that 6x to the 4th term. That single term, the one with the highest exponent, is the only one that really matters in the long run. And this is the magic of Big O. It gives us permission to be lazy in a really smart way. It lets us ignore all that other noise. We don't even care about this 6 out in front. We just boil the whole thing down to its essence and say its performance grows on the order of x to the fourth. That's its growth family. That's all we need to know.
So why should you care about any of this? Well, check out this chart. For an input size of 100, an ON algorithm takes about 100 steps. Makes sense. But an ON squared algorithm? Whoa, that takes 10,000 steps. As you scale up, that is the difference between an app that feels instant and one that just grinds to a halt.
Now, Big O is kind of this celebrity of the family. It's the one everyone's heard of. But it's not the only one. To get the full story of an algorithm's performance, you've got to meet its siblings. So you've got the big three: Big O, Big Omega, and Big Theta. They all work together as a team to give you a complete picture from every angle. Here's the easiest way to think about it. Big O is the pessimist. It tells you the absolute worst-case scenario. Your algorithm will never be slower than this. Big Omega is the optimist. It gives you the best-case scenario. And then you have Big Theta. Theta is the realist. It's what you use when the best and worst cases are basically the same, giving you the most precise, realistic description of how it's going to perform. Okay, so let's tie this all together. We started with a simple, kind of annoying word problem, and somehow we ended up in the heart of modern computer science. How does that all connect? It all comes down to translation. It's the same fundamental skill. The mental muscle you use to look at the word of and know it means multiply is the same one you use to look at a 10-term polynomial and say, that's just O of x to the fourth. In both cases, you're using the language of math to cut through the noise and find clarity. And that leaves us with one last, big, fascinating question. From simple words to Big O, we've seen how mathematical language gives us the power to simplify and understand our world. So what's next? What huge, messy, complex system out there, in biology or economics or even our own minds, is just waiting for the right language, the right notation, to finally be understood?